And the idea is that we will be able to leverage the pattern of connectivity in this graph to calculate what we call the importance score of each node. In this case, each node is a web page, and the importance score will be used to rank that page. And what we want to do is to say that let's turn a seemingly circular logic that says important nodes pointing to, say, you being a web page, means that you are also important. This argument almost sounds like a cyclic argument, but in fact we can use it to derive a recursive definition to define an equilibrium. Now, this equilibrium is not the equilibrium of a convergence of an algorithm, like in power control, or the equilibrium of strategic thinking, as in game theory. This is a fixed point equation equilibrium, as we will see in the rest of this lecture. Alright, so coming back to this question, how can we quantify the relative importance of different nodes in a graph? Or more specifically in this case, quantify the importance of each web page. We will see later in lecture 8 quite a few different ways to quantify the notion of importance of nodes in a graph. In today's lecture, we will look at a specific one used by Google. Now, there are quite a few intuitions you can think about this. One is to say, well, you want to quantify node importance, right? So maybe I'll just count how many links does this node have. Well, since this is a directed graph, where each link is directed link, I'll just count how many links point into this node. In this case, there are 3 links pointing into this node, so we call this the in degree. And the out degree is 1, because there's just one node, one link pointing out of this node, and the total degree of this node is 4. Okay, so this is a simple intuition, as we will see that it's sort of getting on the right track, but it lacks many elements for it to be a useful metric.